Hello, physical science students. Today is Forces Part 3. We are wrapping up the content that deals with forces in Unit 1. Today's objective is to understand the relationship between mass and gravity and understand how gravity and friction interact. So, what is gravity? Well, gravity is a force that acts between two masses. It is an attractive force. Gravity will pull one object of lesser mass to the object with a greater mass. Now, typically, gravity acts downwards toward the center of the planet. So, yes, technically, you have gravity on other objects near you, but we don't notice it any pull towards us because the Earth's gravity overrides anything else. But everything has gravity. Now, typically gravity is going to cause the objects to accelerate downwards. This is why when we let something go up high, it falls toward the ground. Now, gravity will always increase with the object's mass. It increases with the mass of the planet and with the mass of the object. Gravity will decrease the further you get from the planet or further you get from the object. So, an object close to Earth has really high gravity acting on it, while an object out in outer space has very low gravity acting on it. So, thinking about that, I've got a question for you. Which astronaut is going to experience the most gravity? So, astronaut or politician? The politician is here sitting on the Earth, the astronaut is in outer space. Who experiences the most gravity? Well, gravity increases with mass, and gravity decreases with distance. So we're going to assume they have the same relative mass. It's that distance that's important. And for this equation or example, the politician is going to have the most gravity because he is closest to the planet. So example number 2, we've got an astronaut exactly halfway between the Earth and the Moon. Which exerts the most gravity on the astronaut? So the distances are the same. The astronaut is equal distance from the Earth and the Moon. Well, that means we need to look at the mass. So gravity increases as the mass increases. Well, the Earth is way more massive than the Moon. That means the astronaut is going to be pulled closer to the Earth or have more of a pull from the Earth and less of a pull from the Moon because the Moon has less mass. Now, with gravity, that actually gives us the concept of weight. So, weight is the force of gravity acting upon an object. So, weight is equal to mass times gravity. Now, here on Earth, the gravity of us is 9.8 meters per second squared. Gravity is acceleration. So this equation is really, really similar to the force equation. Force equals mass times acceleration. Weight is a force. So weight is measured in newtons in science, not pounds. In science, we measure it in newtons. And your weight is a product of the mass, so the stuff that make you up, and gravity. That means if the gravity changes, your weight will change. Um, Look at these images to the right. This particular astronaut, while he was on the Earth, his mass, the amount of stuff that made him up, in his suit and all his fun stuff, is 88 kilograms. But when they take his weight, they take in consideration the force of gravity acting on him. He has 836 newtons of, 863 newtons of force. That's different than on the moon. The moon's gravity is considerably less than the Earth. So the astronaut feels like he weighs less. This is why in science fiction type movies you hear the term weightlessness for people who in outer space because they don't have gravity acting on them, so they feel like they weigh nothing. So the mass is a measure of the amount of matter in an object. And for my astronaut, the mass is the same on Earth and the moon. We measure mass in kilograms, but weight is the force of the gravity acting on that mass of that object. So, Jupiter, if you did not know, is a gas giant. It is considerably larger than Earth. Much, 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 much larger than Earth. If you were able to stand on Jupiter and weigh yourself and compare that weight to your weight on Earth, would you expect it to be more or less? So weight equals mass times gravity. And Earth, your weight is going to be smaller because the gravity is smaller. On Jupiter, well, Jupiter's got a bigger mass, considerably bigger mass. Therefore, it's going to have more gravity. And if it's got more gravity, your weight is going to be larger. So let's look at a couple of calculations. Now, unless otherwise stated, assume anything we're talking about occurs on Earth. If it doesn't occur on Earth, I'm going to have to give you the other place's acceleration. So a woman weighs 557 newtons, and it asks us what is her mass. Well, we can write down our givens. We know that my weight is 557 newtons, and that's weight. We know that it's asking for mass. But in order to solve any of our equations, we need two of the three variables. Weight equals mass times gravity. Well, gravity for Earth is given to you on your formula sheet. The gravity on Earth is 9.8 meters per second squared. So even though we didn't say gravity, it is inferred that you have to use the gravity. So we're trying to find weight. That means I need to multiply my two other variables. We're not trying to find weight. We are trying to find mass. Bad Miss Raines for not rereading the problem. So we are trying to find mass. That means we are dividing the two variables. You can show your calculations like this, or if you really, really wanted to, you could show them in the triangle. You could have your 557 newtons over your 9.8 meters per second squared. Whichever makes the most sense to you is how I want to see your calculations. So handy dandy calculator tells me that when I take those two numbers and I divide them, I get 56.8. And my unit ends up being kilograms because we are trying to measure mass. And mass is measured in kilograms. So our second concept is free fall. Free fall is when the only force acting on the object is gravity. And it's represented by the letter G. Now, on Earth, the gravity is 9.8 meters per second. That is how fast you accelerate due to the gravity on Earth. So if you jump from a helicopter or an airplane, you are accelerating at 9.8 meters per second squared. So your first second, initially jump out is 0. Next second, you've got 9.8 meters per second squared. And then next second, still continuing, 9.8 meters per second squared. This means your velocity is constantly increasing. Now, it is interesting to note that acceleration due to gravity is constant. That means the mass of the object doesn't matter. Both objects are going to accelerate at the same speed. They're going to change their acceleration at 9.8 meters per second. It doesn't matter what the two objects are. So in here, I think I've got an elephant and I've got a bean, or a pea. I don't remember what the little thing was. Their accelerations are the same. They're going to speed up at the same way, at the same rate. And if there was no air resistance, they would hit the ground at the same time. Now, air resistance, we should remember from our first unit on forces, air resistance is a force that opposes the motion of an object through air. It is a frictional type force. And when you have objects going through a fluid, they get to a terminal velocity, and that's when the air resistance, the fluid friction, equals the gravity pulling them down. That means technically they can't speed up forever. They get to what we call terminal velocity. So terminal velocity is the maximum velocity that an object can fall. So yes, if I were to go up to a tall building and I were to drop an elephant and a feather, that feather is going to reach its terminal velocity really quickly because it has a large surface area. So it's not going to get to the same speed as the elephant because of air resistance. That elephant has less air resistance. It's going to fall and get a greater speed because it will continue to accelerate longer. Now, when you have terminal velocity, you have no net force. That doesn't mean you're not moving. It just means you're not speeding up. Your velocity is constant, but you're still falling. Now, here on Earth, everything that we deal with has air resistance. So we can't actually see this in play where objects will hit the ground at the same time. But if we take and we have an object and it's released from rest, my initial velocity, because it is at rest, my initial velocity is 0. So we release it, and initially the air resistance is smaller than gravity. So the object will speed up. At some point, the air resistance and gravity become equal, and the object no longer speeds up. So whatever that velocity is varies from one object to another. I have a short little video clip where y'all can actually see objects without air resistance. So hopefully this works.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems. And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space.
Notice he said conditions of outer space. There is no air in outer space.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now, in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air.
I think that'd be really cool to see. Real life. Big old wall moving.
It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 Militor in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Yes, they're doing this in slow-mo so that you can actually see the objects are falling at the same rate. Notice the feather and the bowling ball stay lined up throughout the entire fall.
Look at that.
They came down exactly the same. Wow.
Look.
That's right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing. Look at that.
That's just brilliant.
So when there's no air resistance, nothing to oppose the motion of the objects,
Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.
so that was Einstein. But, you know, we're looking at Newton's perspective, and Newton's perspective is telling us that those objects are accelerating. They're accelerating at the same rate because there is no air resistance. That is it for forces today. As always, if you're having any challenges with the practice or understanding the content from the video lesson, please hop into my office hours and get some assistance today.